Okay, problem 5. This is the analog for this particular practice exam to the Einstein crystal in the exam 3 practice exam, or the free rotator problem in exam 3 itself. In other words, it's a problem where the purpose is to see if you can solve a problem that hasn't been solved before on your own. So in this case, we're looking at a model for a polymer, a sort of model for a polymer, where the polymer is thought of as being made up of a whole bunch of freely rotating links. And so every one of these links has a single bond that connects it to the next link, and each of those can have free rotation around that bond. And so the partition function that we derived for exam 3, for example, or proved in exam 3 anyway, applies to each and every link. And the problem is to find all of these thermodynamic properties from statistical mechanics using this particular view of the way a polymer behaves. Now let me say right at the beginning that this is a very bad model for a polymer. It's really just a textbook kind of problem, but we can still do it anyway. All right, so in this case, we're assuming that all the links are independent, and that means that the overall partition function for all little n links should be q to the n, or maybe q to the n over n factorial, right? Depends on whether the links are distinguishable or not. But the links are all joined together in a chain, so we can tell this link from this link from this link by the location they have in the chain, and therefore they're distinguishable, and so the correct formula is q to the little n power, period. Now we want to find the average energy, which is the same thing as the thermodynamic energy, and that's minus the derivative of the logarithm of the partition function with respect to beta. And that is equal to minus the derivative with respect to beta of the log of little q to the n power, which is equal to minus n times the derivative of the log of the little partition function with respect to beta. So for that purpose, it's useful to write this overall partition function, well, to write the little partition function really in terms of beta. We have from up above that the little partition function is equal to the square root of pi times t over theta to the 1/2 power. If we rewrite that in terms of beta, we're going to have q is equal to the square root of pi times t, which is, let's see, t is equal to 1 over k beta. So this becomes 1 over k times theta to the 1/2 power times 1 over beta to the 1/2 power. That should be the most useful form to plug in there. If we take the logarithm of that little q, that's the logarithm of all this stuff. So pi k theta to the 1/2 power minus the logarithm of beta to the 1/2 power, which is equal to the logarithm of all this stuff, I won't rewrite it now, minus 1/2 times the logarithm of beta. And now we just have to take the derivative with respect to beta. So the average energy, or the thermodynamic energy, is equal to minus the derivative with respect to beta of all that stuff. And now you can see why I didn't write out all these constants in here both of these times. And that's because when we're taking the derivative with respect to beta, all that stuff's going to disappear anyway. So this becomes, the minus signs cancel now after that disappears, and we just get 1/2. Sorry, we've got the n up here, so the n there, got to put that in. So there's an n here. Times n times the derivative of that with respect to beta, which is just 1 over beta, and that is equal to 1/2 nkt, which we could have written down right from the get-go, right? Because we know that each rotator contributes 1/2 kt to the overall partition function, and there are n of them, and they're all independent, and so 1/2 nkt we could have just written down right from the beginning. Anyway, The problem actually asks for the molar energy, and to get the molar energy we have to multiply by Avogadro's number, and so that's our molar. Let's put a bar on top to indicate a molar quantity. So molar thermodynamic free energy. That's just going to multiply this by Avogadro's number. All that's going to do is turn this K into an R. So we have 1/2 nRT for, finally, our thermodynamic free energy for the contribution of all those rotations to our polymer. The next thing we want is the CV. And that's just the derivative we want the molar CV, the derivative of the molar energy with respect to temperature, and so that's just 1/2 nR. That's an easy one. Finally, we want the entropy, the molar entropy, but let's just go for the entropy itself at first. That's minus the derivative of the Helmholtz free energy with respect to temperature. And that is equal to, actually, let's do it the other way. I was going to take all the derivatives and do all the algebra, but there's another way to do it. The entropy is equal to, let's see, it's equal to, well, let's do it this way. The Helmholtz free energy is equal to U minus TS, right? And if we put bars on all those, that would all still be true, so it's all true for molar quantities too. Therefore, S is equal to, swapping around, U minus A divided by T. And we have U now, and A is easy, right? And so S is equal to U divided by T minus A is K log of Q, KT log of Q, minus KT log of Q divided by T. And so that's U over T, the minus signs cancel, the T's cancel, plus K log of Q. Now we just have to plug in. So S is equal to, for U we have 1/2 NKT divided by T plus K times log of Q to the little n power. That is equal to, T's cancel, 1/2 n times K plus n times, little n times K log of pi T over theta to the 1/2 power. And that finally is equal to 1/2 NK plus, I'm going to bring the 1/2 down here, 1/2 NK log of pi T over theta. That's almost all of it. We want to turn this into a molar quantity, so we want to multiply by Avogadro's number, and so the molar entropy then becomes 1/2 nR plus 1/2 nR log of pi T over theta. And finally, just to make things slightly neater, let's factor out this 1/2 nR that appears in both terms, and we get a final expression of 1/2 n times R times log of pi T over theta plus 1. Some of that algebra was just to make things neater and wasn't really necessary for a correct answer, but anyway, there we go. And that's it. The problem doesn't ask us for to evaluate at any temperature or anything like that. It just asks for expressions, so we're done.